Okay, so this is another type of counting here. We're going to look at just this one set of problems here. Suppose you got a square area, it's going to be fenced in, and you're going to paint the fence. And it's patriotic. We're going to do red, white, and blue. All right. So the thing is, red, white, and blue. But maybe you don't have to use them all, right? Maybe it could all be red. That's one of the possibilities. So you have red, 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 red for the four sides, or blue, 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 or maybe you have red, blue, red, blue, right? You have a red, blue, and a blue. And the question is, how many different painting patterns are possible? So first of all, assume there's no restrictions in the colors, and you can tell which side is which. So you get side 1, 2, 3, and 4 maybe. Okay, that's to make it a little easier, that first question. So if you want to pause here, go ahead and do it. Think about it. And really, you have four sides, and we can tell the difference between them. And for each side, we have three colors to choose from, right? So it's really just 3 for the first side, times 3 for the second side, times 3 for the third, times 3 for the fourth, right? So that's 3 times 3 times 3 times 3, or 3 to the fourth power is 81 combinations. Okay? Now, it gets a little more complicated if we start, putting some stipulations in there, or start saying, hey, what if we can't really tell the difference, right? Like, you get your four sides, and it's a square fence, and there's no gates maybe, and I don't know, so each side looks the same, right? So I give this example, blue, blue, red, red is the same as blue, red, red, blue, right? Because if you take blue, blue, red, red, oops, I kind of cut that corner at the end there. So there's blue, blue, red, red, right? And then if you look at blue, red, red, blue, well, blue, red, red, blue would look like this maybe. Blue, red, red, blue. But if you take this one and rotate it 90 degrees that way, it's the same thing as this one, right? So they're indistinguishable, so that it really doesn't count as different, right? So the sides are considered indistinguishable. Now that said, when I say the sides are considered indistinguishable, there's a difference between having two sides that are next to each other and two that are across from each other. So blue, red would be different, right? Like this one can't be rotated to look the same as one of these two. So it's really that rotational symmetry where, or maybe not rotational symmetry isn't the word I want, but rotational equivalence. If rotating gets you from one to another, then they're not really distinguishable. Okay? So this is a tougher question. And remember, we have three choices for each side. So you might start with that 3 to the fourth equals 81, but then you kind of have to ask yourself, how many did I double count, right? Like, these would be two different painting combinations up here in these 81 possibilities. But I don't want to count them as two different ones. So, first of all, what if they're all the same? This is one way to do this, is to kind of break it up into different parts, this problem. So if you paint all sides of the same, that's either red or white or blue. Did we double count any of those? If we went red, 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 was it different if we started on like a different one? And the answer is no. Like red, 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 red means there's only one way to do that, right? You pick each side to be red. But there's also a way to pick all four to be blue and all four to be white. The point is, though, there's no double counting. No repetition to subtract. No redundancy, however you want to think of that. So all the same is fine. Okay, now what if we have, so that's one color, right? Those are the one color combinations. What about two colors? And again, if at any point you feel like you have a spark of inspiration here and you think you know what to do, by all means pause it, try to do the problem on your own. So what if you only have two colors in the mix, right? If we only have red and blue like this, or if we have blue and white or blue and red, now, how many different ones are we really counting as the same that we should be subtracting, right? So we had this example, red, red, blue, blue. I'm going to use 1 and 2 right now. so it's not specific to a color. So we've got 1, 1, 2, 2 is one organization, and then we've got 1, 2, 1, 2 is a different organization. And the issue here is that I'm going to move this next line here. Oops, well, I guess I'm not. No, I am. I just have to do it differently. Make some room here. Okay. I say these are two different organizations because, well, these are different. This is what we're talking about here, right? This is different than these two, but these two are the same. I'm using 1s and 2s, and then I'm going to generalize for the different color combinations in a minute. But the 1s and 2s keep it general, so this could be any two colors. And I guess the question is, how many, if we have a pattern like this, 1, 1, 2, 2, how many different times did I count it up here, right? So 1, 1, 2, 2, we already mentioned is the same thing as, oops, as 1, 2, 2, 1. Right, I'm just kind of rotating here. So I'm rotating it through here and taking the first one back to the end. And that's how you get from this one to here. And then we could do it again. We could do 2, 2, 1, 1. That's really the same. And if we go one more, 2, 1, 1, 2, that's really it. Because if we go one more, we're back to where we started, right? Each one of these is going to be counted different up here, counted differently, right? So if this was red, red, blue, blue, red, blue, blue, red, blue, blue, red, red, and blue, red, red, blue, they're all the same because you can rotate from one to another, but they all were counted separately up here. And you can kind of, again, you can kind of see, like, that's the 4 rotations, right? If you take this and you rotate it around 90 degrees 4 times, you're going to go through each of these 4 patterns. Okay, now this one's a little different. This one, if I rotate it once, I get 2, 1, 2, 1. But because of the way these numbers are laid out, if I do it again, I'm back to where I started. So here there's really only the 2 that are the same as each other, right? But there's actually one more arrangement here that I didn't list yet. What if you're only using 2 colors, right? But 3 of the sides are one color and the other side's the other, right? So then we've got this 1, 1, 1, 2 pattern, right? And you know, you can rotate that one 4 times, right? Because it could be 1, 1, 2, 1, or 1, 2, 1, 1, or 2, 1, 1, 1. And those are all the same, right? Once you pick your 1 and your 2. And so, again, with these, you know, when you're counting your combinations, you know, it might be helpful to look at each of these separately. You know, first let me go back to the all the same. I don't know if I mentioned this already, but there's all the same. That means there's one color, right? And there's really just 3 ways to do that, right? There's red, there's white, and there's blue. With 2 colors, we've got sort of 3 different arrangements here, but then you got to consider the color possibilities, right? So with this arrangement, it's really just pick your 2 colors, right? Any 2 colors, it doesn't matter which one's 1 and which one's 2, because you know, if you pick like red is 1 and blue is 2, you don't want to like count it twice and say, well, what if blue is 1 and red's 2? Because if we do red is 1 and blue is 2, we have the reverse of that built in here, right? 2, 2, 1, 1. So if it's red is 1 and blue is 2, then we have red, red, blue, blue. We also have blue, blue, red, red already covered. Okay, so there's really only 3 ways to pick 2 of the 3 colors, right? When you pick 2 colors out of 3, you're also picking the one that you're not picking, right? You're like choosing which one not to pick. So there's 3 ways to do that. Okay, and if that doesn't convince you, there's blue and red, there's blue and white, and there's red and white. And that's it. So there's 3 ways here with the color combinations. And then here it's also 3 ways. Because again, you're picking your 2 colors, and it doesn't really matter which one's 1 and which one's 2 here either. On this one, however, it does matter, right? Because the 1 is different than the 2 because there's 3 of the 1 and there's 1 of the 2. So now we have to pick the first color, and then you also have to pick the second color. So you have to pick there's 3 choices for which color gets to occur 3 times, and then once you pick one color, there are 2 colors left to choose from to be the other color that there's only 1 of. So there's actually 6 ways to make that happen. And so at this point, we've got these all really counting as 1, and these really counting as 1, but there's 3 of them, so it actually counts as 3, and then 3 here, and then 6. So there's going to be 12 distinguishable, rotationally ways to paint this fence, right? Now, this is vague up here. Suppose the sides are considered indistinguishable. I'm gonna say rotationally here. Just use that word. Okay, and I'll get at that when we get into 3 colors in a second, because that's going to matter. But it's what we're saying is, like as I explained before, if you rotate the fence around and you can get a different one of these 81 combinations, it really doesn't count different. So when we take that into account, there are 12 ways to use 2 colors to do it that are actually different. Now, if we, again, in the 81 up here, that actually would have been 4 times 3 is 12, plus 2 times 3 is 6, that's 18, plus 6 times 4 is 24, so 18 and 20, 42 different ways, right? I'm going to put the 42 there of the 81, just to keep in mind. The 3, this wasn't double counted at all, right? It's all red, all blue, or all white. Those were each counted once up here. So we're up to 45 of these 81, but really it's only 15 distinguishable based on the way we define this. Now we're on to 3 colors. And this is really, this part of the second question is really the whole last question also. If we have to use each color once at least, then hey, we got to use all 3 colors. Okay, so we're going to kind of answer the third question as part of the second question. So if we're going to use 3 colors, then one color is going to have to be used twice, right? So we'll just do the 1, 2, 3 again, and we're just going to assume that 1 is the one used twice. And then later on at the end, we'll figure out like how many different ways we could assign the colors, kind of like we did here, right? So what's possible? Well, we can do 1, 1, 2, 3, right? And if we go through the rotations of that, right, if we kind of keep sliding to the left like we did before, then we get what? 1, 2, 3, 1, 2, 3, 1, 1, and 3, 1, 1, 2. Then we're back to where we started. So this is one way. And if we just kind of switch this, flip it backwards, let's say 3, 2, 1, 1. And this is why I put this word in here, rotationally indistinguishable. This is a reflection now, right? This is a reflection. This would be like having blue, blue, red, white, and comparing that to white, red, blue, blue, right? So like white, red, blue, blue. And if we could rotate that, whoops, didn't mean to do that. If we could rotate this, nope, just this guy. Well, it's not going to let me, but I should have drawn this differently. Here, let me just draw it differently. Okay, I'm on blue. just for clarity here. So since they go around in the opposite order, it's like there's like a mirror image here, right? If this is the mirror, and those are distinguishable according to my definition here that I've kind of explained verbally. You could frame the problem so that those should be indistinguishable too, and then you got to think about it a little differently. It makes the problem different. But for our purposes, we are counting these as different. Again, the rotations, if you slide them to the left, we get 2, 1, 1, 3, 1, 1, 3, 2, and 1, 3, 2, 1. Notice this 1, 1, 3, 2 and this 1, 1, 2, 3. Those are, we just really switched the 3 and the 2 there. Okay. So those are all the possibilities where the two of the same color are adjacent, but there's also the possibility that you could have them, separated. So if we had like 1, 2, 1, 3, and we rotate that one, then we get what? 2, 1, 3, 1, and then we get 1, 3, 1, 2, and then one more 3, 1, 2, 1. And notice on this one, it really doesn't matter which one's 2 and which one's 3 because 1, 2, 1, 3, 1, 3, 1, 2. So swapping 3 and 2 doesn't get you a different. These are the same still because of the way that when you rotate, right? In other words, if we had like up here, if one of these was white, blue, blue, and then white and red, if you flip that around, then you'll have blue, blue, and then red and white. And it's the same thing rotationally. So this is really just 3 more possibilities, right? 3 more arrangements, but then we've got the color choices. And really the only choice we have to make here is which color occurs twice. So there's 3 ways here, three kind of like arrangements, patterns, and then there are 3 color arrangements for each one of those because we can choose which color is going to occur twice. So it's really just 9 ways to do that. And that's because, again, it doesn't matter which one's the 2 and the 3 on either one of these, right? Like if we did, let's say white was the one, white was the one that occurred twice, and then we have blue, red. Well, I've got the red, blue covered right here, right? I've got the 1, 1, 3, 2, so I've got white, white, blue, red, and I've got white, white, red, blue, both covered in these 3 combinations, or these 3 permutations. So, so it's already in there, right? So we really just have to pick which color occurs twice, and then the different patterns with the other 2 colors occurring once are all already listed. So altogether, if the rotation doesn't give you something different, we're really looking at 3 and 9 and 12. We're looking at 24 different, for the second question here, 24 different arrangements or painting arrangements that are possible. Didn't write that very neatly. Let me try that again. 24. Okay. Is the answer to that question. And let's just make sure really quick that we actually counted everything, all of those 81. So I mentioned here we were up to 42. 3 where they're all the same color, and then we had 42 just from the 2 colors, right? We had 3 times 4 plus 3 times 2, that's 12, and 6 is 18, plus 6 times 4, 24 here, and so that was 42 ways there, plus 3 there, so that's 45 of the 81. And then here we've got 3 times these 12 arrangements, that's 36, so that's like a 36 plus that 45, right, the 42 and the 3, and that does add up to 81. So that's all 81 arrangements, but 24 distinguishable, and 9 of them if each color has to be used at least once. So it's a pretty complicated problem. I might have gone a little crazy with video number 2 in the series here. We started to talk a little bit about permutations and combinations too, which I'm going to dive into in later videos. So, but they were small numbers, so you could kind of brute force them here without needing any formulas. Anyway, get to the next one sometime soon.